Hello, everyone. I'm Lanyue. Today, I'm happy to talk about our project, Physical Disentanglement in a Container-Based File System. This is a joint work with Yupu, Thanh, Summer, and our advisor, Andrea and Remzi Arpaci-Dusseau. Isolation is an important property in modern systems. Isolation is required for independent failures and recovery in a shared environment across different components, users, and workload. Isolation is also important for avoid performing interference in virtualized environments in multi-tenant systems. We are already living in a world full of isolation techniques. Virtual machines and Linux containers provide an isolated environment for applications. BSD-JL sandbox isolate untrusted applications. Even in the multi-tenant system in the cloud, they will isolate resource for different tenants. However, file systems still lack isolations. Local file systems are the core building blocks of operating systems. They manage user data. They are long-standing and stable. They are also the foundation of modern distributed file systems, such as Google File System and HDFS. Existing abstraction in local file systems only provide logical isolation. Files, directories, namespace only provide logical illusion for users. Physical entanglement across files, directories in local file system will prevent the true isolation to be realized. I will talk about entangled data structures and entangled transactions. Local file systems tend to use shared metadata for multiple files. For example, every file has an inode. Multiple files probably store the inode in the same block. So in here, we have a 4K inode block, and we have two unrelated files. Their inode may be stored together in the same disk block. So if you have any I/O failure related to this inode block, both files will not be accessible. If you have any single bit of data metadata corruption in the same block, the whole file system may have required to check for consistency. There are many other structures are entangled in the file system, like bitmap, directory blocks. So the problem is the fault in this style of shared structure can lead to shared failures and shared recovery for all the files in the file system. This goes beyond to shared method structures. It also relates to how the file system do the I/O. So in the EC3 and the EC4 file system, a shared transaction is maintained for update from all the files. So you have two different files, they update by different workloads, they also have their own dirty data. If one workload wants to force one of the files to persist on the disk, the whole transaction have to be flushed together. So a shared transaction will lead to entangled performance for unrelated files in the same file system. So to solve this entanglement problem in the local file system, we first propose a data container abstraction called Cube. Based on this Cube abstraction, we built a file system to disentangle data structure and the transaction within the same file system for different containers. And this can provide better reliability and performance isolation. We will show that IceFS can have benefits in local file system. They can provide isolated failures for different files. They can provide up to 8 times faster recovery, even up to 50 times higher throughput for certain workload. And IceFS is also useful for high-level applications. In a virtualized environment, IceFS can reduce the downtime of the service over 5 times. If running HDFS over IceFS on local nodes, it can improve the recovery efficiency over 7 times. So this is the outline of the talk. Now I will first talk about the concept of file system disentanglement. Then I will describe how we build a IceFS based on these concepts. Finally, I will discuss some evaluation results and conclude. We propose a data container abstraction called Cube. A cube is an isolated directory in a file system. Each cube is physically isolated on disk and in memory. Let's look at a simple example. You have a directory trees. You can say, I want to put directory B and a subdirectory at cube 1, and cube D and a subdirectory D and another cube 2. They are not only logically isolated as we view in the directory, they are also isolated on physical device. That means different cubes will not interleave with each other. They will not share any disk blocks. To support this data container abstraction, we have to disentangle structure. We follow 3 principles. The first is no shared physical resource across different cubes. That means each cube will have its own metadata, have its own data blocks, no sharing across different cubes. The second is we don't want any dependency across cubes. That means one cube will not have any reference to another cubes. For example, for the linked lists and the tree structures, they encode in dependency in their design. So we have to partition this shared structure into multiple smaller ones for each different cubes. A typical example is in the directory trees. To access a file in a traditional file system, you have to access all the directory entry up to the root directory. Any failure happen along this directory path, you cannot access files. We also don't want any entangled updates for different cubes. So each cube will use its separate transactions. Because we isolate transactions for different cubes, so we also can enable customized journey mode for different cubes. Now I talk about how we build a disentangled file system we call IceFS. IceFS is a data container-based file system. It can provide isolated reliability and performance for different containers in the same file system. We introduce 3 principles, techniques: physical resource isolation, directory indirection, and the transaction splitting. We built a prototype based on EH3. So the related system component we modify, including local file system, the VFS in the kernel, and the user-level tools. Now let's first look at how the EH3 lay out the data on the disk. So in EH3, a disk is divided into multiple fixed-size block groups. So they have a shared CPU block at the beginning of the disk. Then the rest of the space will partition the block groups. And each block group has its own metadata and data blocks. Metadata include group descriptor, the bitmap, and inode. However, the block group doesn't provide true boundary across different files. That means different files can collocate with the same block group, and one large file can span across multiple block groups. In IceFS, we won't provide isolation for different data containers on disk. So each cube will have its own metadata and its data blocks. This is the layout of IceFS. We also have a shared CPU block at the beginning, but it only stores static information, like the fixed number of blocks, fixed number of inodes. And the following shared CPU block, we have a sub-CPU block areas. This will store all the cube's sub-CPU block. So for each cube, it has its own sub-CPU block, and it also has its own block groups. And for sub-block, we'll store the cube-related metadata. Now let's look at how we do the directory indirection. For the same example, we have 2 cubes. So for every cube's top directory, in this case, is directory B and directory D. Actually, their path names are stored persistent on the disk in the sub-CPU block. Basically, like /A/B and /D are stored on disk. So the first step during the multi process, IceFS will load all the cube's path name from sub-CPU block on the disk into the memory. So in this case, we have /A/B for cube 1 and /D for cube 2. At the runtime, if you receive an IO request, say user say I want to read files /A/B and B2, and we'll do a path name prefix match for all active cubes in the memory. In this case, you will match cube 1. Then IceFS will directly jump to cube 1's top directory, B, and doing the directory traversal from there. So any failure outside of this cube will not affecting accessibility inside the cube. Now let's look at the transaction management. In the ES3 and ES4, they tend to use a shared transaction to manage updates for multiple files. So each file's dirty data will managed by a shared transaction. If one workload calls say one persistent file 1, then the whole transaction will be persistent on the disk. This will have this entangled performance problem as I said before. In IceFS, we don't want this problem to happen. So assume we also have 3 files, but each file is stored in a different cubes. Each cube will maintain a separate transaction in the memory. So now every file's updates will be managed by its own transactions. Now if you want to persist in certain files, we'll only flush its own dirty data on the disk, and will not affect other files' dirty data. So in this manner, we can have isolated transaction performance for different files in the same file system. Once we isolate data structures and transactions for the different containers, we can enjoy lots of benefits. First, we can have a localized reaction to failures. Now, if you detect any metadata corruption or runtime evaluation violate, you don't need to enforce global failure for the whole file system. You can have a per cube read only or per cube crash. And this also can encourage developers to put more runtime checking in the code. Because each cube has its own isolated metadata, so every cube can be viewed as basic checking units instead of the whole file system. And this manner can be done both offline and online. And finally, because each cube has its own running transaction, they can do the transaction commit in parallel. And even better, each cube can use its own specialized journey mode to describe its own consistency and perform the trade-off, instead of using the same mode for all the files. Now I show some very simple evaluation results. So we asked several questions. The first question we ask is, does IceFS can provide isolated failures for different files? So we inject about 200 faults, including metadata corruption, metadata read IO failure, metadata write IO failure, pointer failure, and memory allocation failures. So we inject to one of the cube in IceFS compared with inject to random data in the ext3. So basically, we can have per cube failure mode. Basically, like we can have one cube as read only, we still can write to the rest part of the file system. The second question we want to ask is, does IceFS can have faster recovery? So here, let's first look at the recovery performance in the ext3. So in this graph, the x-axis we show the different file system size. The y-axis we show the file system check-in time for ext3. So first, we can see that the file system check-in time of ext3 grow linearly with the size of the file system. So basically, this style of file system checker is not scalable with the increase of disk capacity and the file system size. Even you have a small piece of metadata corruption on the disk, the whole file system have to be forced to scan. So this will take a long time. In IceFS, we create multiple cubes in the file system, and we also inject some metadata corruption with one of the cubes. Now, when we do file system recovery, we can know where the corruption comes from, and metadata is also isolated, so we can do a partial recovery for a cube. So in this graph, we can see IceFS file system check-in time is significantly faster than ext3 because it only need to check partial of the file system. And also, the check-in time of one cube of one user is independent regardless of the rest of files in the same file systems. So IceFS can provide independent recovery for a cube in the file system. Next question we want to ask is, does IceFS has better transaction performance? So we run two simple workloads. The first is a database application SQLize. It sequentially writes large key value pairs asynchronously. The second one is an email server workload, VMware. It's a random write a lot of small blocks and then call fsync after each write. Now let's look at the performance in the ext3 first. So here, we first run two applications alone. Like we first run SQLize, it gets 140 megabytes per second. Then we run VMware, it gets about 20 megabytes per second on an SSD device. Now we run them together, and we can see that both application performance suffers significantly, especially for VMware. Its throughput only have 1/10 of the original one. The reason is, when the VMware call fsync, it have to force the shared transaction to the disk. The shared transaction will include a large amount of dirt data of SQLites. So VMware's performance degrades significantly because of the large delay of fsync. So shared transaction can hurt performance, especially for the VMware. In IceFS, we run these two applications in two different cubes. Each cube has its own running transactions. So in this manner, we can see that both application performance get higher compared with ext3. For VMware, its fsync now is much faster because it doesn't need to force the data of SQLites. For SQLites, it can buffer more data in the memory for better sequential throughput. So in IceFS, we can do parallel transaction to provide isolated performance for different applications. Journey file system use journey mode to provide consistent guarantee for different files, like metadata consistency, data consistency. However, in modern file system, a single journey mode are enforced for all the files in the same file system. So this doesn't provide flexibility for different users and for different applications. In IceFS, because we isolate each cube, so each cube can have freedom to choose what they want. So in here, we show experiment. In here, with first two bar, we run the two applications in the same ordering mode. Order mode basically provides the default metadata consistency. If you want higher performance for SQLize, you can say, okay, for SQLize, I prefer higher performance. I can sacrifice some consistency. So when we run SQLize with no journal mode, it can double its throughput. We also can do this for VMware. We can see the VMware throughput is increased over 50 times because it can avoid a lot of the overhead in the transaction. So specialized journey in the IceFS can provide flexibility between consistency and performance for application and the users. So last question I want to ask is IceFS useful for high-level applications? Let's look at the server virtualization environments. there are multiple virtual machines. Each virtual machine has its own virtual disk files. Here, we assume all the virtual disk image files stored in the same shared file systems. From the perspective of VMs, they assume they have isolated storage, isolated file systems. However, their virtual disk files are entangled in the shared file systems. So any failure or recovery in the shared file system will impact all the virtual machines. Isolation, an important property for virtualization, is not preserved. Let's look at a very simple experiment. So in this experiment, we run 3 virtual machines in the ext3 file systems. On the x-axis, we show the timeline. On the y-axis, we show the aggregate throughput of 3 virtual machines. From time 0 to 50, all 3 virtual machines run correctly. At time 50, we inject a metadata corruption in the file system. And the ES3 will detect that in the runtime. It will remark itself as read-only. Then all the 3 virtual machines cannot write to the file system anymore, and they will crash. Then after the crash, the file system have to do the check-in. This FSCK will take over 500 seconds. After the check-in is finished, then you boot up 3 virtual machines again. So we can see in this case, you have a large service downtime for these services. We can do better in IceFS. We can provide a cube to protect them for different virtual machine disk image. Like in this case, we can put in the 3 cubes. Now every cube, any failure related to any cube will only affect itself, will not affect the rest of the file systems. So we do the same experiments. From time 0 to 50, they run normally. At time 50, we inject a metadata corruption in the VM1's virtual disk image. In this case, we have 2 options. First, we just shut down the file system. We run FSCK, but we only check 1 cube instead of the whole file system. So the file system checking time is much shorter. After the checking is finished, then you boot up all 3 virtual machines run again. We even can do better because each cube's metadata is isolated. So when we detect the cube 1 is corrupted, we can shut down cube 1 and run FSCK for cube 1. At the same time, allow cube 2 and cube 3 still running. So in this case, VM2 and VM3 still can serve a request, and we run checking for VM1. And this can even improve the availability of the services. So we show that local file system isolation is also very good for high-level services. To conclude, local file system lack physical isolations. We show the physical entanglement problem in the shared metadata and the transactions. This can cause reliability and performance problems. We build an IceFS file system based on data content abstraction can provide better reliability and performance isolation. Looking ahead, as the workload world moves to the cloud, as the computing moves to virtual machine and containers, as the multi-tenancy world becomes the only world we are living in, isolation is the key property to give you the illusion that you have your own machine. However, the system underneath our application have to rethink isolation in very fundamental levels in terms of how they lay out their data, how they do their I/O. If they don't, then they will see the same entanglement problem in today's talk. Our source code will be available soon on this link, and now I'm happy to take questions.
Hi, Bill Belowski, still with Microsoft Research.
Okay.
So how do you allocate physical space between the cubes? Like, how do you decide what block groups the cubes get? And is it dynamic?
Okay, so the first you create a cube, that's like create an empty directory. There are no space allocated. Then you put file in the directory. It first found a empty block groups. Once you found the first empty block group, assign that block to belong to that cube. We store a cube ID in the block group metadata. So then if you have following file in the same cube, you see whether you have free space in already allocated block group. If you have, then you store there. Otherwise, you find the next empty block groups.
Okay, so then you basically have a global level of metadata about the block group allocations. So do you wind up with problems maintaining that correctly?
Not really, because when we allocate block group, actually we just scan the disk, found the first empty block groups. We will not use any shared metadata. Each block group is self-defined. They have its own bitmap. They have its own group descriptor. Different block group will not share any metadata.
Well, I mean the allocation of the block groups itself to the, like when you're assigning block groups to cubes.
Yeah.
Right. You have to make sure that a single block group is assigned to at most one cube. right?
Yes.
And so there has to be some metadata that keeps track
Yeah,
of that.
yeah.
How do you handle corruption in that?
Yeah, so for inside every block group, we store a cube ID to tell the block group this block group belongs to cube I, this block group belongs to cube J. Then when you allocate a file for one cube, you match the ID where the ID matches. If it doesn't match, you know this block group doesn't belong to you. Then you find the next empty block group or existing block group within the same cube.
Okay, thank you.
Yeah, thanks.
Yang from Penn State. How do you handle cases where there is a link from one cube to another cube, like hard link or software symbolic link in file system?
So I answer this question in two aspects. First is like currently we don't support hard link. There are many other references like we talk in the paper. For example, if you have one inode in cube 1, and every inode have lots of blocks, if you have any corruption, the one inode probably point to a block in a different cube. This is called cross-reference. So we can detect that when we do some I/O, we can check whether this I/O or target destination belong to the same cube. If not, then we can detect it in the wrong time.
So do you simply block it?
I'm sorry?
Do you simply block it? Block the hard link from one cube to another cube when you detect it at one time?
So currently we don't support hard links. Yeah.
Okay, thanks.
So the correctness, the isolation seems quite nice, but I'm concerned that some of the performance and tweaks might be giving up semantics, specifically the POSIX security checks, and also, I mean, what do the fancy journaling modes do to the correctness of varmile under failure conditions?
So like for each cube, we store its journey mode in the substitute block. So basically, like if one cube uses data journeying, then in the runtime, its transaction will journal both data and metadata. Another cube will say, if I don't use any journal, then we'll not use transaction to manage its data. And if that cube crashes, then in the runtime, we just run normal FSCK for that specific cube. But for the other cube, we can replay the transaction for that. So we can support different type of the journey mode in the same file system.
And the security semantics?
Excuse me?
POSIX defines hierarchical security semantics where you have to check the permission bits all the way down.
That's a good question. So one way to solve that is like, so in current Linux, if you check permission, you usually check with one step by step during the directory traversal. For us, we can store the most strict set of permission in the cube top directory. So basically, when you jump to the cube top directory, you first check whether you satisfy all the previous permission bits. If you're not, then you return error code. Otherwise, you can continue within the cube.
Thank you.
Yeah, thanks.
Two more questions, and remember to say your name and affiliation.
Yang from Columbia. So my question is, how do the cubes scale up? For example, ideally I want to have a different cube for every file or every directory of my in the file system. And does that work? If it doesn't, is it possible that I can just have a bunch of different partitions and mount them as separate partitions, and that would work, I think.
Okay, actually I have two questions. First question is like, how can you create different cubes? Basically, like we provide a mechanism, like our implementation based on directory. You create directory, you say, okay, this directory is a cube. Then you put a file in the cube. So basically, you can, within the same directory, you can put a lot of files, or you also can put just single files. For the second question is like, how it compare with partitions? Actually, this is a very frequent question people ask. So basically, like, if you use partitions, then you can create multiple file systems on different partitions. Yes, you have isolated disk space. The method graphing will only within the partition. However, it also have lots of other disadvantages. First, you waste a lot of storage space. And if one of the file systems within one of the partitions called panic, you crash the whole operating system, you're still affecting all the file systems in the same systems. And also, it still have slow recovery, because if one of the file systems on partition have corruption, you still have to scan the whole partition. If partition is large, you still have a slow recovery. And also, it's hard to manage a large number of partitions. You have to have a root permission to create partition on the systems. And even worse, it's hard for high-level applications to use that. For example, if you run a HDFS, they want to use local file system, it's hard to allow them to make a partition on the local node. So our cube don't have this kind of disadvantages.
We have time for one very short question.
Okay, this is Zilin from NetApp. So I got a question about performance.
Okay.
Seems your evaluation is running on an SSD.
Yeah.
So I wonder what the performance will be like on an HDD, because seems this will increase the number of disk 6. Is that correct?
So there is some trade-off. For example, we run the same SQLite and the VMware on the disk. Actually, performance of S3 become even worse because the disk is more slow. You have to flush a large transaction. It takes longer for everything. So VMware is even worse. But originally lot of organizations in the file systems are optimized for hard drive. That's why they use the bundled transactions. They won't get more data flushing at one time. But once we have faster device, the bottleneck shifting from the device to the software itself. That's like we show in the transaction bundle in the IceFS. So we believe that with the faster hardware, IceFS will be much more better. Yeah.
So you mean this is designed for the SSD instead of hard drive?
Well, we also work in the hard drive.
Okay,
Yeah.
thanks.
All right, thank you very much.